Teams that chase correlations without understanding them end up deploying dashboards and models that fail in production when the data shifts a little. The mistake is thinking the correlation coefficient is a universal strength meter that works for any pattern you throw at it. What is actually going on is that the coefficient only counts how much two variables move together along a straight line after removing their units, and it can be hijacked by outliers or by a narrow slice of the data. Picture yourself scanning a report, seeing a big positive correlation next to a glossy scatter plot that quietly curves, and approving a plan that will drift off target the moment new cases arrive. Here's the right mental model. The correlation coefficient measures how often and how strongly two variables sit on the same side of their own averages at the same time. You take each value, subtract its mean to see if it is high or low, scale by its spread so big units do not dominate small ones, and look at the product of those scaled deviations. When the deviations share a sign, the product is positive. When they oppose, it is negative. When one or both are near the mean, the product is small. The coefficient is the average of those products across the cases, so it summarizes alignment of ups with ups and downs with downs. Because you standardize both variables before multiplying, the coefficient drops all units and becomes a pure comparison of shape. Double every x value or shift every y up by a constant, and the coefficient does not change because scaling and shifting are erased by the standardization step. That is why it is bounded and interpretable across different measurements and contexts, and also why it can feel slippery if you expect it to carry information about slopes or units. A useful geometric picture is that you are comparing two standardized lists as directions. The more they point in the same direction across cases, the larger the coefficient. Use a concrete example. Suppose you track weekly ad spend and weekly sales for the same product. On weeks where spend is above its own average, do sales also land above their own average, and by how much relative to their typical spreads? If those ups and downs tend to happen together, and by comparable amounts, the correlation is large and positive. If higher spend weeks tend to coincide with lower than usual sales because of a promotion that moves demand across weeks, the coefficient will slide negative. If ad spend moves independently of factors that actually drive sales, the average product of the standardized deviations washes out toward nothing. Here's the most common beginner error. They look at a curve relationship, like a U-shape or a saturation curve, and interpret a correlation near zero as evidence of no relationship at all. The coefficient is not designed to see curvature. It only weighs how much a straight line through the data captures synchronized deviations. If the pattern bends, the positive and negative parts cancel, and the number hides a strong but nonlinear tie. The cost of that mistake is practical and painful. You leave signal on the table because you trusted a metric that is blind to the kind of structure you actually have. Forecasts that should hedge for curvature instead double down on a flat trend. You might underfund a channel at the very range where it starts to work, or keep funding it past the point where it saturates, simply because the coefficient stayed modest while the true pattern was not. The correction is specific. Always pair the coefficient with a plot of the data, even a quick rough one, before making a claim about strength. If you see curvature, transform sensibly or fit a model that can bend, and then examine the correlation of residuals with predictors to check whether you have removed the main structure. If the transform scatter is roughly linear and homoscedastic, the coefficient now says something aligned with what your eyes see. If not, move to models that respect the shape instead of forcing a line to explain it. Another mistake is to ignore outliers and leverage. A single extreme point with unusual x and y can drag the line toward itself, inflating the average product of standardized deviations and making the coefficient look impressive when most of the cloud does not agree. Or a point far out on x, but near the mean on y can pull the slope and still leave the coefficient misleadingly modest, depending on the rest of the structure. Heavy-tailed distributions and clumps of data with different spreads create the same kind of distortion. The fix is a small checklist. Compute the ordinary coefficient, then compute a rank-based alternative to see whether the story depends on exact distances or just on ordering. Refit with the conspicuous points removed once, not to erase them from truth, but to ask a diagnostic question about an influence. If the story flips, call it out and investigate the cause. Check whether the scatter splits into groups with different centers. A single coefficient across mixed groups often reports a relationship that each group individually does not have, or misses a relationship that lives within groups. Now connect correlation to regression without hand-waving. If you regress y on x with a straight line, the slope is the correlation multiplied by the ratio of the spread of y to the spread of x. That tells you the coefficient does not carry units, but it does scale the slope when you put the units back. And if you standardize both variables first, the slope of the best fitting line through that standardized scatter is exactly the coefficient. And the fraction of variability in standardized y captured by that line is the square of the coefficient. That also explains why the sign of the coefficient matches the direction of the fitted line. A vector view makes the intuition tighter. Think of each standardized variable as a long arrow, whose components are the standardized scores for each case. The coefficient is the cosine of the angle between those arrows. When the arrow for y is almost a projection of the arrow for x, the angle is small, and the coefficient is large and positive. When the arrows are nearly opposite, the coefficient is large and negative. When the arrows are at a right angle, the variables are uncorrelated, which means the best linear prediction of one from the other is essentially a horizontal line around the mean. There are structural traps that quietly dampen or inflate the coefficient. Restriction of range is the classic. If you only sample honor students or only look at marketing spend in a narrow budget band, the standardized deviations shrink and the apparent alignment weakens, even if in the full space the relationship is strong. The inverse happens when you pool different subpopulations with different means. Across the pooled data, you might see a strong overall trend that disappears or reverses when you look within each group. Correlation answers a precise question about the entire set of paired values you fed it. Change the slice of the world, and you change the question. Correlation is also not causation for a technical reason, not just a slogan. The coefficient cannot separate direct alignment from alignment induced by a common driver because it only inspects the joint pattern of two variables. If temperature pushes both ice cream sales and beach attendance, the standardized ups and downs will march together even though neither one causes the other. To make causal claims, you would need designs or variables that break those confounding alignments, and the coefficient alone will not provide that. Sampling adds another layer of fragility that most dashboards hide. With something like 10 paired observations, the sample coefficient jumps around from batch to batch even when the underlying relationship is steady. The standard error of the coefficient depends on the sample size and the underlying alignment. So small samples amplify noise and generate false confidence or false doubt. This is not a reason to ignore the coefficient. It is a reason to treat a single estimate as a draw from a distribution rather than a fact carved in stone, and to ask for intervals or resampling checks before acting. Build a reliable workflow. Start with a plot and a quick read on whether a straight line is a sane summary of the cloud. If yes, compute the coefficient, then inspect sensitivity to obvious outliers into subgroups. If no, bend the model or transform the variables until the pattern becomes roughly linear and stable in spread, and only then let the coefficient summarize strength. Keep units in mind when you move from correlation to slope. The first is unitless alignment. The second is how many units of change one variable tends to deliver per unit of the other under a linear assumption. When in doubt, report both and show the scatter, because i's plus a precise scalar beat the scalar alone. The most important shift is to stop treating the coefficient like a universal thermometer for relationships and start treating it as the average handshake of standardized ups and downs along a straight line. It measures linear alignment, not general dependence, not slope with units, not cause. Once you hold that model in your head, you know exactly when the number speaks for your data and when it is out of its depth. Next, we tackle sampling. Why a small group can represent millions, because without understanding how a handful of cases can estimate the world, every correlation you compute will feel shakier than it needs to.